fully charged, there is a lot of talk about electrification. But of course, that implies the use of batteries, and a battery is still fundamentally quite a mysterious thing. We learn at school that the point of a battery is to take stored chemical energy and turn it into electrical energy. So there must be chemical reactions involved, but there's no pipettes and no test tubes, none of that stuff you'd see on a lab bench at school. So how does that actually work? And more importantly, how is it going to work in the future, and how much better can a battery really get? So we're here on the University of Warwick campus. I've just seen some graduating students wandering past, but you've got very close ties with industry, and so actually what you've got here is the whole chain. You've got academic research, the pure stuff, you've got applied research, you've got actual industry users coming in, all, you know, right the way through the chain. And that must give you huge advantages in finding out what's going on.
Indeed, it's fundamental to have, if you like, input and support and collaboration between all those different aspects. So our industrial partners who set the context and the problems that we need to solve, through to the academics who've got that pure science background that grounds the work that we do.
And we've got this big WMG building behind us. Tell me a little bit about WMG, what it does, you know, the big picture stuff.
Okay, so here at WMG we work with industry to solve problems, and at the moment the big focus is on energy storage and how we can translate the chemistries and the battery types that we know today into something that will basically be usable in the future for automotive, for grid storage applications and so on. Traditionally we've been working with our automotive industrial partner, but as the batteries develop and their capabilities improve, as I said, it's opening up opportunities in other industries. So in recent years we've started working in rail, in marine, in aerospace and in wearable electronics as well, and wearable batteries. To cope with that, what's happening is we're developing new chemistries, new types of batteries, new battery designs. It takes roughly 5 to 8 years for an experimental chemistry to make it through into the marketplace. So we will see lithium-ion chemistries and those derivatives around for a long time to come. But over time, with these different industries using energy storage, we'll start to see other chemistry types and other flavours, if you like, of battery technologies appearing in the market.
I'm off to meet Alex Roberts, who's one of the lead engineers here, and he's going to show me how these batteries are made. So this is where it all begins?
Yep, this is a typical graphite material, active material you'll find in the anode for the vast majority of lithium-ion batteries.
I like touching things, but I know I'm in a chemistry laboratory. I shouldn't touch anything.
Shouldn't touch.
Never
I mean,
touch.
this is fairly innocuous. This is the same material as you'd find in a HP pencil. Basically, it's dug out of the ground and purified.
You know what's brilliant about that is that, you know, we're in a very modern laboratory. You do lots of things, but fundamentally grinding things and polishing things. I mean, that's what you did to materials 100 years ago. But because we live in the physical world, you absolutely have to do it now.
Yes, I mean, there's a lot of different ways that you can make some of these materials, but the go-to method for a lot of the established chemistries involves heating up to maybe as high as 1,000, 1,200 degrees, and then grinding down. So you get the different components to react together at very high temperatures, and then you need to turn it into a nice fine powder that we can process it into actually making a battery electrode.
So this machine's next, is it?
Yes. So this is our reel-to-reel coater. So what you have here is what we would call a reverse common roll setup, where we'll take our electrode inks and we'll put them onto a metal foil. So as you can see inside there, we have a copper foil. This is set up ready to coat an anode.
So it's pink. It's very rare you see pink metal, but that will be
indeed,
copper.
yeah, this is very, very high purity, very high grade copper, which is a nice thin foil. That's about 12 microns in thickness.
Really?
Yep,
That
as
is
thin as that.
super thin.
Yep.
Okay, that's impressive.
The roll will rotate and we will coat a thin layer of ink onto that roll. The copper foil comes in the other direction, and we transfer the ink from the roll onto the foil.
So you've got a 12 micron thickness of copper, and then how thick is the layer of ink on top of that?
That's one of the places that we can vary this depending on the material we're using, depending on the final cell that we look at. Okay. So the rule of thumb is if you want a higher power cell, one of the things that you would look at changing is making a thinner coating. If you want a higher energy cell, you'd make a much thicker coating. And then
this thing over here is the last bit, is it?
Yes, this is where we take our coated electrode foil and put it through a calender. For this calender, it's very similar to an old-fashioned mangle, a very precise version where it's got two large steel rollers, and they apply a pressure under heat across the profile of the foil.
So are you squashing it thinner, or are you
You
processing
squash it all thinner, and by doing that you increase the density of the material you've just put down, so you can get more into the same volume, and you also increase the adhesion between the layer you've put down and the foil underneath. Across the width of an electrode foil will give about 3 tons per centimetre of compression, so it's quite a lot of compression.
So all these things that say don't put your fingers in it, they really mean it.
You really don't want to put your hands anywhere near it.
Okay, so what I love about all of this is this combination of extremely fine control and sort of very modern science, and fundamentally we are gluing carbon to a piece of copper and putting it through a mangle. We still live in the physical world, but it's amazing those two things are possible.
There's a huge amount of background science that goes into it and understanding that goes into it, but the processes are quite simple. There's a lot of control that goes into there as well. We're going to go now into a dry room. So inside there, one thing that batteries really hate more than anything else is moisture. So the place where we assemble the batteries is a dry room environment.
So normally, you know, there's water in the air all the time,
Yep.
we don't really notice it, but in there is almost nothing.
Yes, we will be the wettest things in there. So we have our anode material, which you saw being coated before, you can see on copper, and then we match this up with a cathode. So this has got a different active material on there, and we coat it onto aluminium. What we now need to do is stack these up one on top of the other in a very precise way, and we need to put a separator material in between the two. The separator material stops these two physically short-circuiting.
Right.
So it's electrically insulating, but allows the electrolyte material and the ions in there to pass through it freely. And what you can see here, if I just start it running, is it's going to take an anode and a cathode from the back.
It's like robots, there are all these little things moving around. I expected, you know, sort of nano manufacturing and all of these complicated things, and I'm sure that does exist,
Yep.
but this is much very plonk a thing on top of another thing.
Well, this is what they call a Z-fold arrangement, because you get the Z-fold of the separator material. The machine you see here, the stacker, is one area where we're looking a lot at the next generation. It's one area that is a real hold-up in manufacturing. So a lot of the larger manufacturers have got a lot of know-how and expertise in changing these materials so they go much faster. So we then heat seal around three sides. So you can see we end up with something that looks like this.
Little packet.
Okay,
yeah.
so a little packet. And you end up with what we call a gas bag on the top.
I know
so
people
this
like
area, this area here, when we take our electrolyte and we fill it in, so the liquid component goes into the battery, we then need to do a very slow charge and a very controlled charge and discharge to get the chemistry that happens inside the battery started. Suck all of that gas out there in a very controlled environment, and then put a final seal on the top. So we have something that looks like this.
So now
this is a final battery cell.
On the table between us, we've got a battery, even though it doesn't look much like the sort of batteries we buy in the shops, but this is the crucial part of technology, right? So tell us a little bit about what it is and how it works.
Okay, so this is a lithium ion pouch cell. It's an A5, just like paper, format cell that you'd find typically one of these in an electric vehicle. Within these electrodes, we have a lot of particles that store lithium. They store it reversibly so that when you charge and discharge a battery, the lithium ions will move back and forth both electrodes.
You know, this is a chemical reaction, and so ions, which are charged atoms or molecules, are actually things are physically moving inside this system.
Absolutely, yes, they move back and forth, these electrodes, and in the meantime will drive a current, and that's what gives you your energy. And the way the materials can reversibly accommodate the lithium, let's take for example in an anode, which is the electrode printed on copper, the negative electrode. If you have graphite, which is still the main material of choice, it's a layers of carbon atoms, and so because to the small ionic radius of the lithium atom, it can fit quite nicely between the graphite sheets. And so for every 6 carbon atoms, you can accommodate 1 lithium.
And then there's one other thing.
The other thing is the key thing, it's the electrolyte. which is currently a number of organic solvents with a lithium salt dissolved within them, which is your source, the main source of lithium ions.
And so, it's important that it's liquid because then things can move. So
Absolutely. Given how many lithium atoms have to move, lithium ions have to move, they need to move effortlessly. And so certain solvents favour that. In terms of safety developments going forward, people are developing non-liquid electrolytes, so solid electrolytes, which will be non-flammable. And so the challenge there lies in how fast we can move lithium ions through them. And that's why there is still, the majority are based on solvents because of the speed of lithium ion transfer. What
needs to get better to make a better battery? Because the fundamental drawing hasn't changed, but the details have, haven't they?
They have indeed. Firstly, the energy storage systems of Galvani and Volta, they weren't reversible. So that's the difference, and the difference between lead acid and primary batteries. So that is the major step change difference that became commercialised in the early 1990s through Sony. But the efficiency we've referred to as the coulombic efficiency, that's the charge in versus charge out ratio. And there are a number of things that happen there. Initially, when you first charge a battery, if this is the surface of your materials, some of the electrolyte solvent breaks down at low voltages because it's not as stable. So what happens is you get breakdown of some of the solvents and the lithium salts, and you get what is called an SEI layer, which stands for a solid electrolyte interface. Mm-hmm. And that is being researched a lot.
So you get this extra little layer, you've got all this nice structure, and then once you start running it gets coated with stuff.
That's right. And this coating, it's beneficial in one respect because it passivates the surface of the materials, but it also acts as an irreversible loss of lithium. And when you think of lithium being your charge currency, when you start to lose it, and this continues over time, and this is one of the challenges that leads to inefficiencies in batteries.
So that's one of the ways batteries can degrade.
Absolutely, especially if these active materials are prone to volume expansion, then they'll start cracking, you get more surface area. The more surface area you get, the more SEI you get. But also, one of the other major physical artifacts within batteries is when you start getting cracking. And so you start isolating lithium, and that leads to continuous capacity fade, which is why you get a limited cycle life on a lot of batteries. And that is the major hurdle to overcome in all, from portable devices to vehicles. The range needs to be longer, therefore the cycle number needs to be longer.
So with this basic idea, you've still got a lot of chemistry and physics go. How much better can it get? Let's talk about the future a little bit. What new things are coming along? What advantages do they have? What is the future of a battery going to look like?
Well, a lot of people are working on advanced divergences from classic lithium ion. Metal air batteries have the potential to deliver a lot of energy, but the power density is quite low. And so whilst there is a lot of interest in such systems, they are still some way off being commercially viable. So there are a number of different chemistries, such as lithium sulfur, which can hold a lot of energy, but their reactants, they can be quite unstable within the electrolyte solvents.
And then there's things, so for example, so lithium is a little atom or an ion that can move about, but there are other small atoms like sodium and magnesium.
That's right.
How are they going to be used?
Well, sodium, it's not as energetic as lithium, so its energy density will be somewhat less, and it's a slightly larger ion, and so the materials it can interact with will be different to lithium. But the beautiful thing about sodium ion is that for things that don't require mass reductions, i.e. for non-mobile things.
So if you can have a big heavy battery that just sits there.
Absolutely, and for grid storage, for example, for load levelling on the grid system, if you can have huge banks of sodium ion cells sitting and merrily cycling away for tens of thousands of cycles, because a lot of sodium-ion chemistries are stable. And sodium, obviously, very abundant.
And cheap.
And cheap. So there is a lot of active research developing sodium-ion.
One of the big questions around new battery technologies, which is what you make them from. And, you know, elements like cobalt, for example, we know that they're in these batteries and they have their problems. What are the options for sorting out that problem?
Okay, well, in the first branch of lithium-ion chemistries, the cathodes were based on lithium cobalt oxide, so transition metal oxide. And cobalt has inherent toxicity issues and not terribly straightforward when we come to recycling battery. So ways that people are trying to overcome the issues with cobalt is working on different cathode chemistries. So to achieve higher rates of performance within batteries, researchers developed lithium iron phosphate, and there are other transition metal oxides such as lithium manganese oxide. The key is it's always a trade-off with energy density and power, but a lot of research groups and industry are looking at alternative cathode chemistries for this very reason.
We're standing next to this thing that looks like an oven, except it's a lot shinier than my oven. What is going on in here?
Okay, so this is where we start to test the batteries that we've either developed or we've had delivered to us. Batteries are increasing in their power and energy density all the time. So when they can handle more and more power, it means that they're also generating more and more heat. So we have to understand how quickly the heat's generated, where it's generated and so on, so we can inform the thermal management side of the equation. And then the final aspect is the mechanical behaviour as well. When a cell is charged and discharged, it will actually expand and contract quite significantly, and we have to characterise that behaviour as well, because that then plays into the mechanical design of your battery module and then ultimately the battery pack. The aim of the laboratory here is to charge and discharge those batteries in a very controlled way. So where we can safely use the cell and at which point we have to stop either charging or discharging, how quickly we can charge and discharge, and how hot or how cold the batteries can be used. So temperature plays quite an important aspect in the behaviour of a battery.
So, and you've not just got one of these. I mean, there's a whole row of them here.
Yep.
So this is a scaled up operation. It's lots of batteries tested in lots and lots of different ways, and just data flooding in.
So we've expanded rapidly over the last 5 or 6 years. The facility we're in now is probably 4 times the size of the facility that we started with. We're just adding new laboratories as we speak. So in a couple of weeks we'll have a new, what we call aging and degradation laboratory, which is probably 10 times the size of the laboratory that we're in at the moment. There is an insatiable demand for battery testing capability in the industry, particularly as we move into the world of new chemistries, new applications and so forth. We're one of the largest open battery testing facilities in the UK. We're UK government funded, which means any company within the UK is able to come in and use these facilities, and it's the way that the UK government is trying to drive innovation and new battery manufacturing in the UK.
And what would you like to see? If you know, 10 years down the line, what would be the thing that the problem that you hope is solved? What's the thing that you just, that is the sort of itch you want to scratch?
That's a really good question. The work we do here is looking at really 3 aspects of battery behaviour. One is the performance, better range, better energy, more power. One is safety, and the other is cost. And classic engineering compromise, generally at the moment you can't have all of those, so you have to decide which of those is your priority. But as we improve our knowledge of how to build batteries, the costs will reduce. We're using newer materials, will improve the range and the performance, and also consider the safety. So my my dream ticket would be a vehicle that will recharge in 5 to 10 minutes, give me a 200-mile range, and is intrinsically safe.
We've inadvertently set this up as a market stall. We're not actually selling batteries here, but we've got examples of different ways of putting things together inside these big battery packs, right? Which is something called the format. So tell me a little about what that is.
In the industry, there are essentially 3 different flavours or shapes of batteries that the customers and the different industries can use. So the first shape is what's known as a cylindrical cell. It's a cylinder, so that electrode material that you saw being manufactured before It's wound on a bobbin, so essentially a sort of Swiss
It's kind of
roll,
like Swiss roll, yeah.
and it's then put into a metal can, and that's probably the traditional battery that most people will be familiar with.
So that, if you're going to use those, so this Tesla battery famously uses
So
these.
you can see the Tesla battery uses the same format, so it's got these small cylindrical
so
cells.
just stacked up like lots
Yep.
and lots and lots and lots and lots of them.
Thousands and thousands of these cells are used within the Tesla. This is one module, and there are many of these modules that then form the complete vehicle battery pack.
So it's a very sort of brute force approach. We're just going to put more little batteries
Yep.
to make a big battery.
So there are advantages in terms of cost and the availability of that sort of form factor, but there are disadvantages as well. So if you can imagine putting cylinders together in
Right.
a particular shape, sometimes you'll lose volume.
Not so efficient.
So it's not so efficient. There are advantages though, because the cylindrical cell itself being a metal can gives you mechanical strength, so your module design is made that little bit simpler.
So that's one of the other options. So if someone comes along to our market stall, doesn't fancy the cylindrical option,
Yep.
the pouch is an alternative.
Yep, it's a much bigger battery, so one of these cells is equivalent to probably 10 of the cylindricals,
Yeah.
so it gives us more power, more current, and being a flatter shape, it's much easier to thermally manage, so we can get heat in and out of this
Right.
much better.
So it looks much better for stacking it up. It looks like a sensible shape.
It's a sensible shape in terms of stacking, but from a mechanical perspective, this material is quite sort of structurally flimsy, so from a mechanical engineering point of view, that engineer has a slightly more difficult task creating a package that will accept these sorts of cells.
We've got cylindrical cells and pouch cells, and the last thing on our market stall is over here.
And that's a prismatic cell. So a prismatic cell is essentially a sort of a hybrid of those two different types. So what we have is a roll of the electrode material, so it's wound almost like a cylindrical cell, but then imagine that being flattened down and then placed into a metallic box effectively. This gives you the advantage of it being mechanically rigid, so mechanical design is much easier, and being flat you can take energy or thermal temperature in and out a lot easier as well.
So even inside these, we've got battery packs from different cars here, but inside they've got one of these three. There's only three
that's
options.
Right. So chemically they're identical. It's just simply down to the manufacturer's choice or priorities in terms of thermal management, power handling, mechanical design, which might send you in one particular direction towards a cylindrical cell, a pouch cell, or a prismatic.
It's been so exciting to see the work that they're doing here, and especially to hear about the ideas that are coming down the line for the future. It's clearly a place to watch. If you enjoy Fully Charged, you can support through Patreon, and the details for that are all in the description below this. I'm Dr. Helen Czerski. Thank you for watching.